Welcome back. In the last lecture, we started discussing 5 basic problems on convex sets. And these are going to provide a framework that we're going to use for a number of combinatorial optimization problems, but also they really show the power of the ellipsoid algorithm. So in the previous lecture, we listed out the 5 problems: optimization, violation, validity, separation, and membership. And we mentioned we're going to only focus on the first 4. So we're not really going to talk about membership, though it is possible to talk about results about that. And so there is we've got optimization, which we've already talked about in the last lecture. We have the violation problem, which I'll talk about in more detail in this lecture, the validity problem, the separation problem, and then membership. And you can think of these as problems, but we're also going to think about having an oracle for optimization, or an oracle for the that solves any one of these problems. And it is in this sense that we want to compare computational complexity, or let's say the hardness of any one of these problems. Meaning, if I have an oracle that solves the optimization problem, can I use that to solve the violation problem, only making a polynomial number of calls to that oracle? If the answer is yes, it means that violation is not a harder problem than optimization, and similarly throughout. And so you can, thinking back to the lectures on ellipsoid algorithm, what did those rely on? Those relied on the separation problem. There was a separation oracle as a key step to the ellipsoid algorithm. And what we're going to do is use the ellipsoid algorithm to solve other of these problems using a separation oracle. And that will show that those other problems are not more difficult than separation. There's a natural hierarchy here that you would guess. What's surprising, and again, it comes thanks to the ellipsoid algorithm, is that all of these are equivalent, especially the top 4. To make membership equivalent, we need something extra, and we're not going to focus on that. So let's get into where we left off. The previous lecture talked about optimization. Now let's talk about the strong and weak violation problem. So it's as follows. So the strong violation problem says is as following: given a vector in Rn and given gamma, some real number, decide if C transpose X is less than gamma. Oh, and of course, let me go back a slide here. So throughout all of this, we're assuming we have a convex set K contained in Rn. So decide, the strong violation problem is defined by K, a vector C, and a threshold gamma. And the problem is to decide whether C transpose X is less than gamma for all X in K. And if not, find a Y in K with C transpose Y bigger than gamma. So one thing that you should note right away is that this is this is certainly implied by optimization, and we're going to write down these implications later. But if you have an optimization oracle where you give it a vector C and a convex set K, and it returns the maximum value it can take, it immediately solves this problem, because if it tells you that the optimal solution is x star and C transpose x star is less than gamma, then that is basically the first, it answers affirmatively that indeed C transpose x is less than gamma for all x and k. And then if it's bigger than gamma, then it's provided you that y. So another way to think of this is that this violation problem is really just the decision version of linear optimization. So if we take linear optimization and we turn it into a decision problem, then this is it. And you can also see that certainly for the weak violation problem, which I'm about to write down, and the weak optimization problem, violation can then imply a violation oracle gives us an optimization oracle by simply just bisection. So bisection on gamma, the threshold. So let's now write down the weak violation problem. I think you'll get the spirit of how we go from weak to strong. It's basically turning every statement of optimality and feasibility into approximate and satisfaction of constraints into approximate feasibility, approximate optimality, approximate satisfaction of constraints. So the weak violation problem, or creatively named WVIOL, says given again, it starts in the same way. So given a vector in Rn, that would be our objective, given a threshold gamma, and now it's a rational number, but also given a positive margin of error. I'm using this notation, so it's a rational number that's positive. Then either one, assert that C transpose X is less than or equal to gamma plus epsilon for every X, not in K as we have here, but every X in the deep interior of K as we defined in the previous lecture. Remember, a point X is in the deep interior if a ball of radius epsilon for a fixed epsilon is contained in the set. And we denote it by this way, minus epsilon, whereas positive epsilon, which we're also going to use, is for the epsilon expansion of a set. Okay, so what does this mean? This is basically saying that C transpose X less than gamma is almost valid for every single X in our set. In particular, it's almost valid for every single X in the deep interior, or find some Y that's almost in K. In other words, it's within the epsilon expansion of K with C transpose Y bigger than, and you can guess what's going to happen here, not gamma, as is written above, but gamma minus epsilon. So it's just the softening of all of these constraints. So so it's saying either assert that the given inequality C transpose X less than gamma is almost valid for almost every X, or find a Y that's almost in K that almost violates. So that's what this is. Validity is exactly like this, like violation, except it doesn't ask you to produce that Y. So the strong validity problem, or just SVAL for short, says given a vector C in Rn and a threshold in R, decide if C transpose X is less than gamma for all X in K. So flipping back for a moment just to look at the violation problem, it's exactly the same. It's just not asking us to produce a Y in the event that the answer is no. And in weak validity, the weak validity problem is again exactly what you would expect. So we're now not only given a optimization direction, C, we're not only given gamma. I'm calling it an optimization direction because it's convenient to think about the violation and the validity problem as decision versions of optimization. Another way, and really where the name comes from, is just I give you a constraint, C transpose X less than gamma, and you need to decide whether it always holds or not. So given a C in Rn and a threshold, weak of course means that everything needs to be in Q. That's the whole point of defining weak, so that we don't have to deal with infinite precision arithmetic. A threshold, gamma in Q, and also my epsilon, that is a positive rational number, then either 1, assert that C transpose X is less than gamma plus epsilon for every X in the deep interior, or assert that C transpose X is greater than gamma minus epsilon for, let me write Y there, for some Y in S K positive epsilon, the epsilon expansion, but no requirement for the weak validity problem to actually produce that Y. Separation. We've already seen this when we were talking about, and we've seen a specific example of this when talking about the arborescence problem. So this problem says, given Y in Rn, decide if Y is feasible. And if it's not feasible, prove it by providing a separating hyperplane. So you should think about this as the violation problem, as dual to the violation problem. And if not, find some vector in Rn such that C transpose that given vector Y is bigger than the max of C transpose X such that X in K, or really what this is saying is that C transpose Y is bigger than C transpose X for any X in K. And the weak separation problem says, given a vector Y, a rational vector, given a threshold delta that's rational and positive, then either 1, assert, so this is the approximate version of both of the options above. Either assert that not Y is in K, but that Y is in the delta expansion of K, or produce a hyperplane. Find C, find a C rational vector, and we can normalize C here, such that C transpose Y is greater than or equal to C transpose X minus delta for every X in the deep interior of K. In other words, find a C that defines an almost separating hyperplane. So now let's look back at the 4 oracles, and let's note their relative strength. So some things are pretty straightforward. So strong optimization clearly implies, so what these arrows mean is that if I give you an oracle that solves a strong optimization problem, then you can solve the strong violation problem. And the violation problem is more difficult than the validity problem because violation is actually asking you to produce the point that violates. So whereas validity does not. So clearly we have this, and also for the weak versions as well. So weak optimization gives us weak violation, which gives us weak validity. With a bit of thought, and again, I mentioned that the second arrow, the second implications here are basically immediate. Note that by bisection, we also have. Well, let's get to that in a second. So with a bit of thought, you can also show that an optimization oracle, the weak optimization oracle, implies the weak separation oracle. So I'll let you think about that. So now let's talk about what other arrows we can fill in and ask, okay, so I mentioned that weak violation is the decision problem, or that the violation problem is the decision version of optimization. So naturally we would think that we should be able to solve the optimization problem, certainly at least the weak optimization problem, if we're given an oracle for the weak violation problem by bisection. So we should have this arrow, at least, by bisection. But just a moment of thought tells us that we actually need a little bit more. We need at least to make sure that we start in the ballpark of the right answer. So certainly this is true as long as we have some side information, and I will denote the side information just by an R here. So this R is too many arrows here. I'll just write it in words. For this implication, we need a circumscribing, or we need the radius of a circumscribing ball. And if we have that, then the weak violation problem can be used to solve the weak optimization problem by bisection. So we need this. So basically, so we have this arrow as well. I'll put an R. So this is the state of affairs. We didn't talk explicitly about how weak optimization gives us weak separation, but this is basically what we've got. Okay, so let's go back to the ellipsoid algorithm and basically see what we get here. So what ellipsoid algorithm does for us is that it gives us this important arrow: weak separation to weak violation. So this is what we get by ellipsoid. And once we get this, we actually have quite a bit. So let me redraw the picture. So adding this, we now have weak optimization implies weak violation, which implies the weak validity problem. The weak violation, if we have an R there, tells us that we can get a weak optimization oracle. Weak optimization gives us weak separation. What's written above here is that weak separation gives us weak violation, as long as we also have an R. We can show that weak validity, as long as we have an R, and I'll let you think about where this comes from, gives us the weak separation problem. So basically what this tells us is, so again, let me write explicitly here, R denotes this R denotes the side information that K is contained in a unit ball of radius R around the origin. So I want to tell you the idea of this arrow here, because this is important, and it's basically the key part that will tie everything together. And basically now we know that everything is equivalent. These 4 weak problems are now all equivalent. Certainly, if we have this side information. So let me give this idea here for how we use the ellipsoid algorithm. So what is the problem? We need to solve the weak violation problem, the decision version of the optimization problem. And we have a weak separation oracle for K. So using the weak oracle, I'll denote it in this way. For K, how do we do that? We're going to do the following. We're going to make a weak separation oracle for a new set, K hat, which is equal to K and X, such that C transpose X is greater than or equal to gamma. Because this is exactly, let's remember what the weak violation problem is. The weak violation problem says, I give you a vector C and a threshold gamma, and I want to know, is it true that C transpose X is less than gamma for every point in K? That's another way of asking, is K intersect C transpose X greater than gamma? Is that set empty? And weak violation, in contrast to weak validity, is saying, in addition, if it's not empty, please provide a point. So if this set is not empty, please provide a point. And you can see that this is exactly what ellipsoid algorithm is going to do for us using a separation oracle. So we're going to feed essentially this. I'm not going to give all the details here, but essentially we give this set to our to the ellipsoid algorithm. Now the ellipsoid algorithm needs separation, and all we have is separation on K. That's our assumption. But the set K intersect a half space is also pretty easy to find a separation oracle, because it is K for which we have the oracle, and then just one additional explicitly given half space inequality. And so if you imagine that you want to check whether a point is in a polytope, and I don't give you that polytope, but I give you an oracle that tells you, either you're in it or it tells you violating inequality. And I ask you, are you in that polytope, and also do you satisfy this additional inequality? So the additional inequality, you can just check for yourself. It's easy. We do that computation. So we're the oracle, if you want to think of it that way. Okay, so this is the idea that we basically, if you're given a separation oracle for K, it's easy to then create a separation oracle for K and an additional, and the intersection of additional half space. And now once we have a separation oracle for the set K hat, we're home court for ellipsoid algorithm. Ellipsoid algorithm will either tell us that the set is empty, in other words, C transpose X is indeed less than gamma for everything in K, or it will find a point that for which is in this set, which is exactly what weak violation asks for. So we make a weak separation oracle for K, and then we run the ellipsoid algorithm with this separation oracle for K hat. And that's and this is the story. So this is a really powerful result, and I think that, you know, on the surface it's perhaps surprising that if you have a separation oracle, you can solve an optimization problem. Again, back to our motivation of R arborescences, this is now tying everything together. Remember, we defined this R arborescence problem and notice that it is an optimization problem with exponentially many constraints, but we have a polynomial time algorithm, or in other words, an efficient oracle that we are the oracle ourselves. We can reproduce this oracle that solves the separation problem. And then we took a break and talked about ellipsoid. Ellipsoid isn't exactly talking about optimization. Ellipsoid is just finding a feasible point when you have an exponential number of constraints. And this is basically pointing out actually a pretty simple fact that if you have a way to solve the feasibility problem, then by bisection you can solve the optimization problem at least weakly. So that's the story there, and it ties together the importance to these combinatorial problems of the ellipsoid algorithm. I want to mention just one other thing, and it ties more specifically to polytopes, and I want to define the polar of a polytope, and talk about how separation and optimization and violation and separation are really related through duality with each other, which again shouldn't be surprising. Violation is saying, do all the points satisfy this constraint? If not, find a point that doesn't satisfy it. The dual swaps points and constraints. So the separation problem is saying, is this point feasible? Not, is this inequality always satisfied? Is this point feasible? And if not, give me an inequality that violates it. Violation says, is this constraint feasible? And if not, find a point that violates it. So let me make a definition. If P is a polytope, X such that AX is less than B, so it's a polyhedron, I'm actually not assuming it's bounded, then the polar of P, and this is defined very similarly in spirit to polar cones. Many of you may have seen that if you've taken a class in convex analysis or convex optimization, is defined as B star. Sometimes people use a circle, but it's this all points Y such that X transpose Y is less than 1 for all X in P. And note that this is also very similar to the way that a dual norm is defined. So all of these notions of duality are very intimately linked. And as an example that you should keep in mind is that if our polytope is just the unit box minus 1, 1, not the unit box, but the box of minus 1, 1, then its polar, and you should check this for yourselves, is what's called the cross polytope, or the L1 ball. X such that the L1 ball is less than 1. This is called the cross polytope. And again, note how the role of extreme points and facets is swapped in this definition. So the box is an example of a set that has 2 to the n corners and only 2n facets. The cross polytope is an example of something that has 2n corner points, 2 for every coordinate axis, but you need exponential 2 to the n facets to describe it. And here's the basic result, which is almost needs a little bit of thought to iron out the details, but it's pretty. The intuition is pretty immediate. Solving an LP over a polytope P is equivalent to solving the separation problem over the polar, over P star. This word here, this scribble is over. And just kind of outline the basic proof before we end this lecture. So we've seen that weak optimization is basically equivalent to weak violation using a bisection argument. Again, I'm being a little loose here. I'm not explicitly mentioning the circumscribing ball, etc. So now we're going to show that weak violation is linked via duality and the polar to the weak separation problem. It's kind of a restatement. I guess less a proof. I should have put that above or what we're doing. So the idea is the following. So if we're given P and my vector C, my rational vector, let's consider the weak violation problem. In other words, the decision problem. Consider the decision problem. We want to know is max of C transpose X subject to X in P less than gamma. Let's just normalize and make gamma equal 1 here. I can always do that. I can always normalize C and gamma less than 1. And if not, produce Y in P such that C transpose Y is greater than 1. But note that this max of C transpose X subject to X in P being less than 1, right? If this were to hold, what does that actually mean? That's exactly saying, looking back here, that's exactly saying that C is in the polar. So if this statement here is exactly equivalent to writing that C is in P star. And moreover, what about the second part that we have here? If it's not, what is a Y in P such that C transpose Y is greater than 1? What is that with respect to the polar? It's exactly a separating hyperplane. Y is that separating hyperplane. So moreover, if the answer is no, so if this is not less than 1, then the violation problem asks us to produce a Y such that C transpose Y is greater than 1. So if there exists a Y in P with C transpose Y greater than 1, then first of all we know that C is not in P star, and we know that Y transpose C, I'm writing it in this way to be more suggestive of a separating hyperplane, is greater than Y transpose Z for every Z in P star. That proves one implication. The other implication takes a little bit more care because it's not clear that any separating hyperplane belongs to P, but it corresponds to something in P. I'll let you think about those details. So this is just as kind of a side coda to the story of the equivalence of the 4 major problems. And though we're not going to go into it, I'll just mention that membership is also equivalent if we have an additional piece of side information, the weak membership, which is that we're, in addition to a circumscribing ball, we're also told the radius of a ball that sits inside of our set K. We're not going to. It requires some ideas beyond ellipsoid, so we're not going to go into those, and we're not going to need it so much. So this is the main story, and I will just end again by focusing on this image. These 4 problems are equivalent, and really the main workhorse that shows that they're equivalent is the ellipsoid algorithm. We're going to stop this lecture here, and next time we're going to continue talking about these problems in the context of specifically not an arbitrary set, convex set K, but polytopes that are defined by rational coefficients.